Hello and welcome to this presentation of the STM32H5 public key accelerator, widely used for asymmetric cryptography applications. Public key cryptography is part of many security standards and is widely used to establish secure communication channels across unsecure open networks like the Internet, or to provide authentication via electronic signatures. Software-only solutions can be too slow for real-time applications, impacting the system's overall performance. The PKA module is an efficient hardware accelerator that speeds up the public key cryptography operations performed by the CPU. It accelerates Rivest, Shamir, and Adelman, or RSA, Diffie-Hellman, or DH, as well as elliptic curve cryptography, or ECC, over prime field operations. Supported operand sizes are up to 4,160 bits for RSA and DH, and up to 640 bits for ECC. Binary curves, Edwards curves, and curve 25519 are not supported by the PKA. The list of supported operations are described here. Modular exponentiation for RSA decryption, scalar multiplication, and signature for ECC are protected against side-channel attacks. Those operations are used when manipulating secret keys. PKA lightens the CPU workload by performing key operations in the PKA core using dedicated PKA memory. First, the CPU loads initial data into the PKA internal RAM, which is located at address offset 0x400. Then, in the PKA control register, the CPU specifies the operation which is to be executed and finally asserts the start bit. Once the PKA reports the end of operation in proc end F flag, the CPU reads the resulting data from the PKA RAM, then clears the proc end F flag. Software can abort a PKA operation at any time by clearing the EN bit in the PKA-CR register. In this case, the content of the PKA memory is not guaranteed, except for side-channel protected operation for which PKA memory is guaranteed erased. The PKA has three error flags: the operation error flag, or OPERRF, the address error flag, or ADD-RERRF, and the RAM error flag, or RAM-ERRF. All flags can generate an interrupt if the corresponding interrupt-enabled bit is set in OPRRIE, PROC-END-IE, ADD-RERRIE, or RAM-ERRIE. When the PKA peripheral reset signal is released, the PKA RAM is cleared automatically, taking 667 clock cycles. During this time, the setting of the EN bit in PKA-CR is ignored. PKA side-channel protected operations, like modular exponentiation for RSA decryption, scalar multiplication, and signature for ECC, manages secrets that are automatically erased from PKA RAM at the end of the operation. Here are the modular exponentiation processing times using different exponent and operand sizes. Other important operations like ECC scalar multiplication and ECDSA signature and verification are also mentioned. Values are computed with the clock frequency defined on the slide. Operations protected against side-channel attacks are also highlighted. Thank you for attending this presentation.